Okay, so here we go. 6.5b, number 7. It says a force of 825 newtons is used to push a 100 kilogram box up a 5 meter long frictionless ramp which is inclined at 20 degrees. A says find the velocity at the top. So, make a quick drawing. Here's your box. The problem tells you that our person, presumably Roy, uses 825 newtons to push it up to the top of the ramp. The text of the problem tells you that this is a 20-degree incline and it's 5 meters long. Now, notice, as the box goes up the ramp, you're gaining height, right? So it probably would be useful to know this height. So just use some SOHCAHTOA and you'll figure out that the height at the top of the ramp is 1.71 meters. All right, so are there any problems with what I've done so far? Okay, so you want to think about the motion of the box, and you want to be thinking about height and velocity. So down at the bottom, we know the height is 0, the velocity is 0, so that means that my GPE is going to be 0, my KE is going to be 0, which means that my TE is 0. Yes?
Yes.
All right, up at the top, we know the height, which we could use to find the GPE. Turns out to be somewhere in the neighborhood of 1666. And the problem, if I remember correctly, wants us to find the velocity. All right, so everybody good up to there?
Yes.
Okay, no, remind me to change our 10 minutes later. Okay, so again, like I said yesterday, some of this is just kind of autopilot, right? You think about height and velocity, you go through, figure out as much about the energy as you can. We can't find the kinetic energy here, and therefore we can't find the total. All right, so once you get to this point, your next question ought to be, what do I know about the total energy? So there's two possible answers. Either it's constant or it's not. Is the total energy in this problem constant?
No.
No, because there's a non-conservative force doing work. So having realized that, what should our next step be?
Find the work.
Find the work done by the non-conservative forces, right? Okay, so there's two ways to do it. You can find the change in energy. Is that going to help me here?
No.
No, because I don't know the total energy here, right? So the other option is to do that top equation. So the work of non-conservative forces is, well, for us, it's the work from Roy, right? And the work of Roy is going to be, let's see, 825 newtons times, what do I use as my displacement, you guys? 5 meters, because that's how far it's moving while he pushes it, times the cosine of 20 degrees, right? 0. Okay? Remember, that angle in the theta, or in this equation over here, that theta is the angle between your force and your displacement. All right? And the angle between those two vectors is 0. So this is technically times the cosine of 0, which is just 1, right? So is everybody okay with why that's 0? I'm still seeing people mix that up. Okay, cool. So multiply this out, you get 4,125 joules. So that's the work that Roy did. Let me pause there for a minute. Yeah.
I think the GP is 1676.
Yeah, it depends on how you rounded your height. So, yeah, whatever. Oops. Thank you, though. Okay. All right, everybody good? All right, great. So what the bleep does that mean? Like, why do we care? The work of Roy is 4,125 joules. So Tim, help me out. What's that tell us?
So now we know that, that's our non-conservative force. We know that equals the delta TE, and since the initial total energy was 0, we know that that's going to be the total energy for the last part.
Perfect. And I like very much that you highlighted the fact that the total energy begins at 0. Because a lot of times I see people just assume that the work is the final energy, and that's not always true. Okay. Here it happens to be true because we're starting at 0. But that's not true as a rule. Good? All right, so Tim's exactly right. We started out with no energy. This represents how much we gained. So 0 plus what we gained gives us our final. Everybody good up to there? Okay? So now that I know this total energy, I can subtract to find the kinetic energy, and then use that to find the velocity. Follow? Would it be horrible if I stopped there for that part? I'll do part B, but for part A, is that enough? Anybody need me to do more? Okay. All right, so part B is similar. The big difference is this. Part B has friction. And so what that does is it means that when you get to the top, the velocity is slightly slower than whatever this answer turned out to be. Okay? So I'm going to cheat. Everybody's okay with this? All right, I'm going to do a thing. I'm going to recycle my drawing because I'm lazy. Oh, maybe I'm not. Is it going to let me? Oh, I see what it's doing. Okay, so for part B, it's the same setup, right? You're still starting at rest at the bottom. Roy is still pushing. Everybody good? I'll give everybody a second to get caught up. My chemistry teacher used to always do this, and it used to make me angry. I can't just erase the overhead, Mr. Thompson, I would say. I wouldn't really say that. Do you guys have any idea what I'm talking about?
I don't think the word answer.
That's okay. All right, are we good? Everybody all caught up? Okay, so the problem says, so there's friction, and so Roy pushes it up, but due to friction, the velocity at the top is only 2 meters a second, so slower than what it would have been without the friction, right? And so the problem wants to know how much work, or how much force friction exerts. Okay? So since I know the velocity, what am I able to find that I wasn't able to find before? The KE, right? Okay, question or answer? The 2? It's in the, isn't it 2?
It's 4.
Oh, shoot, I'm sorry. I must be thinking of a different problem. Sorry about that. Thanks, LaShawn. Better? Everybody good? Okay, sorry about that. All right, so now that I know the velocity, I can find my kinetic energy, right? So that turns out to be what, 800 joules, I think, if you find it? Oh, so now I can find my total energy. Just add these guys up, and you get 24, I guess 76 joules, right? We decided this was supposed to be a 7. Good? Okay, so now we're kind of like, now what do I do? Well, once again, my total energy is changing, so what should I do? Anytime your total energy is changing, what should you do? Find the work. Find the work by your non-conservative forces. So for us, I know Roy's force, but I don't know friction. So I don't think I can use this equation quite yet, right? But I know how much my total energy is changing, right? My change in total energy is just 2476 minus 0. Okay? And so that is then, that's the work done by all of my non-conservative forces. Follow? Now, in part A, we figured out how much work Roy had done. That was 4,125 joules. So let's think about this for a minute. So what this is telling us is this. Roy did 4,000 joules of work. He tried to give this thing 4,000 joules of energy. But for some reason, we only gained 2,000 joules of energy. So what happened to the other, whatever, 1,700 joules? Friction. Right? Does that make sense? So I guess if you wanted to write it mathematically, it would be this. You'd go, all right, well, the work done by all my non-conservative forces is the work of Roy and the work of friction. So the work of non-conservative forces is the 2476. The work of Roy is 4125 plus the work of friction. So subtract And you'll find that the work of friction is negative something. I will ask my calculator. 2, 4, 7, 6, minus 4, 1, 2, 5, 1649-ish. And I'm done, right? Because that's friction, which is what it was asking for, right? Good. Yeah. It asks for the force of friction. This isn't the force, this is the work. So now I can use this guy, work equals force times displacement, to find the force, right? Specifically, work of friction is force of friction. Those are F's, really bad F's. So you get 1649 equals the force of friction times, what was the displacement? Do I need to worry about the angle? No, because the motion's up the ramp, friction is down the ramp, so they're anti-parallel, right? So I guess I'll give you a negative force, right? Cool, you guys? All right, so that's number 7. I think that was probably the hardest one on the homework. There was a lot going on there. I guess 6 was a little tricky too. But was it 6 that had the Roman numerals? Yeah, that was 4. All right, anyway, are we good? Problems? Issues? Concerns? Cool. All right.